The speaker is Professor Wang Yao from the University of Hong Kong. His title is Valley-spin phenomena in Van der Waals heterobilayers. Let's welcome him.
Thank you. First, I'd like to thank the organizers for inviting me here. It's my first time to visit this beautiful campus. It's really a pleasure. So in this talk, I will introduce some spin and valley related phenomena that emerge when you stack two-dimensional materials on top of each other to form these so-called Van der Waals heterostructures. This is a brief outline of my talk. First is a quick overview of the building block, the monolayer semiconducting transition metal dicotyledonide. And the key feature that we are interested in is the physics associated with the carrier's valley degree of freedom. But when you stack these monolayers on top of each other, one actually very general feature is they always have this so-called Maury pattern because of the lattice mismatch and the inevitable twisting angle when you do the stacking. So that means locally the atomic registry between the two layers it varies over a long distance. And I will show that the form of the intervalley coupling between the two layers will be controlled by the stacking because carriers are sitting at the corners of the Brillouin zone instead of the gamma point. And because of this stacking dependence of the interlayer coupling, the physical properties of the heterobilayer get modulated in plane. So I will give two examples. One is we look at excons in the so-called type 2 heterojunctions, and we find that the light coupling of excons gets strongly modulated in this in-plane direction, and that leads to quite interesting features such as arrays of uniform quantum emitters, and also exconic superlattice with a very pronounced spin-orbit coupling. The other example system is when we look at the so-called type 3 heterojunction with a broken gap. There is a hybridization of bands between the two layers. It leads to a band inversion. And then this Maury pattern leads to tunable superstructures of the topological insulator because of this stacking dependence of interlayer coupling. So this is our building block. That's a group 6B transition metal dicotyledonide. And the elementary unit is a triatomic plane. But if you look from the top, that's just to the hexagonal lattice. And when you think down to monolayer, there are two important changes compared to the bulk. One is the broken of the inversion symmetry. So this is a bulk unit cell, but the monolayer is just half of it, and the inversion symmetry is absent. The other is a cross from a direct bandgap semiconductor to an indirect one in the bulk to a direct bandgap semiconductor with a visible range frequency bandgap. So that makes this material highly interesting for optoelectronics applications because of this direct bandgap, and that was located at the corners of the hexagonal Brillouin zone called K and minus K points. There were 6 corners, but each group of 3 are equivalent. So altogether, you have 2 valleys, 2 corners called K and minus K. And since the band edge are at these corners, the generic corners, they're also referred as valleys. In an earlier work together with Chen Liu and Di Xiao, we realized that in 2D hexagonal crystals, when you have inversion symmetry breaking, these valleys can pick up contrasted physical properties that is described by pseudovectors. This includes the Barry curvature, optomagnetic moment, and also the one which is also associated with circular dichroism for interband transitions. So this makes it possible to address the valley dynamics by coupling it to the external electrical, magnetic, or optical field. So that gives rise to the idea of using this valley to as another method to represent information in electronics, or now called valley electronics. So in this transition metal dicalconide, we have this inversion symmetry breaking. So naturally, you should expect this valley physics, and microscopically, that can be shown by finding the K dot P Hamiltonian for the band edge carriers, which turns out to be a massive Dirac fermion model. So if you neglect spin orbit coupling for the moment, you may notice this Kp Hamiltonian is simply the graphene, but with a gap term because of the inversion symmetry breaking. So the sigma represents the two d orbitals of the transition metal atom. And for this massive Dirac fermion, our early work has shown that it has a valley contrasted barrier curvature, and since with this barrier curvature, the electron can have a anomalous velocity in an in-plane electric field, but then K and minus K carrier has opposite transverse velocity. So that's an analog of the spin Hall effect, which you may call it the valley Hall effect. And moreover, if you look at the interband transition of this massive Dirac fermion model, you can show that the transition at K valley coupled dominantly to the left-handed circular polarized light, and the other one coupled to right-handed polarized ones. So there is a valley optical selection rule allow you to address a valley using optical method. And also, transition metal atom has very strong spin-orbit coupling, and that gives rise to a very large spin splitting, in particular at the valence band edge. And because the two valleys are time reverse of each other, this spin splitting has opposite sign, which means that the spin index are also logged to the valley index at the band edge. So in this talk, when I talk about the valley, it's actually also spin. The two valley has different spin. So using this optical selection rule, you can you do the optical orientation of valley or spin polarization. Here I use the block sphere representation, where the north and the south pole correspond to an electron hole pair in the K or minus K valley, and other points are the linear superposition of these two configurations. So the selection rule allows you to access these block spheres of north and south pole by circular polarized light, that's valley polarization. And using linearly polarized light, you can also access this equator, which are the superposition, that's the valley coherence. And in this 2D material, it also has a very interesting feature that is a reduced Coulomb screening, and leads to very strong Coulomb binding of the electron hole pair into excitons. So that's a typical experiment that's showing the presence of these excitons by looking at the photoluminescence. This is the vertical axis is a doping, and this is energy. That's experiment from Xiaodong Xu's group. This is a neutral exciton, one electron and one hole bound together, and these are the three particle states, 2 electron, 1 hole, 2 hole, 1 electrons. So the important feature in these excitons, hexons are well studied in gallium arsenide, quantum wells, but the new features in these 2D materials is, as I mentioned, there's a reduced Coulomb screening, so that the binding energy are particularly strong, can be hundreds of millielectron volts. And that also means the bore radius is also much smaller than what you can you expect in gallium arsenide. With this small bore radius, the electron and the hole get larger chance to get on top of each other to make happen this so-called electron hole Coulomb exchange interaction, where one carrier can be scattered from conduction to valence band and the other from valence to conduction band in the other valley. So if you consider this in the context of exciton, that's like annihilating an electron hole pair here and creating one in the other valley. So this exchange interaction is like a transverse coupling between the two valley configurations, and that depends on the central mass momentum of the electron hole pair. So if you work out this dependence, the symmetry dictates that it must have this chiral form with a chirality of 2 and vanishing at the K point. So with this exchange interaction, the Excon dispersion will be modulated into this two split branches. One branch has the interesting linear dispersion, so it's a massless Excon. The other one is a regular massive one, and they have this chirality, that's a pseudo-spin configurations. So this coupling of the Valley pseudo-spin to the Excon's center of mass momentum has several important consequences. One is that it can lead to faster Valley depolarization by this Miley-Silver-Shen mechanisms. So the Valley lifetime is actually very short, comparable to the photoluminescence lifetime, sub-picosecond. And on the other hand, it can also give rise to interesting Barry curvatures and the Excon Valley Hoyt effect. So these Barry curvatures and the Hoyt effect come from the interaction effect, come from the Coulomb exchange interaction, the one that I just explained, exchange between electron and hole. And also if you have, for example, a third particle bound together to form a trion, this one can open a small gap at this previously we have this touching point. But you can, if once you gap it, there will be a Barry curvature appear there. So this can come from the coupling to the third particle in a trion state. So then you can have this trion Valley Hoyt effect. So in this system, there are actually two origins of this Barry phase induced anomalous transport. One is due to the Barry curvature in the Bloch band. The other is from the Coulomb exchange interaction between the particles in a bound state, in an Excon or in a trion. So these are the Valley physics that you can expect in the monolayer. And many of them have already been observed in the experiments, including the optical pumping of Valley polarization coherence, and using the Valley selection rule to do some coherent rotation of the Valley pseudospin, and also the photo-induced Hoyt effect and Excon Valley Hoyt effect. So this is just a partial list. What I'm going to, so the brief message is that there are very rich properties associated with electron holes because they are massive Dirac fermions, and also for Excons, which also turns out to be have the massless or massive Dirac spectrum. So the main focus of this talk is to look at the heterostructures when you stack two modulators into the heterobilayers. And then what matters would be the interplane coupling of the massive Dirac fermions from the two layers. So these are the two, so this interlayer coupling of massive Dirac fermions can be relevant at least in the following two contexts. One is, we know that when you put two TMB together, they usually have this so-called type 2 band alignment, meaning that the conduction band edge is from one layer and the valence band edge is from the other layer. So if you consider excitons in this heterobilayer, then you would realize that the lowest energy exciton state would have the electron and the hole separated into two different layers. That has some very interesting consequence. First of all, this means the exciton has a permanent dipole, electrical dipole, and it couples to a perpendicular electric field. You can tune its resonance. Moreover, there is a dipole-dipole interaction, so exciton interact with each other strongly, and that interaction turns out to be Valley dependent because of the exchange part. And now, so previously I mentioned that Valley lifetime can be short because of electron-hole exchange interaction, but in this interlayer excitons, since electron and hole are separated in two layers, so their overlap get quenched. So the Valley lifetime can be really long for these interlayer excitons, while it can still remain optically bright, and also with a very long photoluminescence lifetime. So that's one. And then if you look at how this interlayer couple to light, then the interlayer coupling would matter as well. I will discuss later. And the other context is you can also apply an electric field, and that will shift the band from the two layers. And you can even close this band gap when the field is sufficiently strong. So then you have this situation that the half massive Dirac from the two layers and it directly overlap and they can hybridize. So that corresponds to the possibility of a band inversion of a massive Dirac cones. So so that's when you look at the heterostructure from the band alignment. But another important feature you have to consider is this it's called Maury pattern that I mentioned at the beginning. So inevitably you will have this Maury pattern because of the lattice mismatch. And the difference would be whether you have a large period Maury or small period Maury. So in this talk, I will focus on the Maury with a relatively large periodicity, meaning that locally you still have approximately atomic registry that looks like a lattice-matched heterobilayer, but over long distance, this registry varies from one to the other. And the key message here is since the banded carriers are located at the corners of the brilliant zone, then the stacking really controls the interlayer coupling, and that leads to the modulated optoelectronic properties. So the two examples, one is the interlayer excons, and the other is the topological band inversion. Okay, so we will see how this Maury modulates the excon properties as well as the properties of the topological insulators. So first, let's begin with the excons. And we can have a comparison of the optical selection rules of monolayers and heterobilayers. So one way to look at this optical selection rule is you just examine using the rotational symmetry. So that's a transition matrix element. And the lattice has this C3 rotation, in-plane rotation. So you can put in these unit operators. And then you end up with this conclusion that for this to be non-zero, then the initial and the final state has to satisfy this selection rule. But in calculating this initial and the final, so these are the quantum numbers of the initial and the final state on the C3 rotation. But in analyzing these quantum numbers, you have to keep in mind that now, since we are looking at the valleys, the block function have this non-trivial phase factor. So these are the Wang orbitals. This is the plane wave phase factors. And when you project these plane wave phase factors at the valleys onto the lattice, then they can contribute these phase windings, which contribute to these quantum numbers. But then this phase winding from this plane wave part, it depends on the choice of the rotation center. Like in this case, these are the same state, okay? But now I'm just choosing this to be the rotation center, then the phase winding is counterclockwise. But if you choose the rotation center to be another side, then it can become clockwise. And also, there's no winding if you made the third choice. So this means this quantum numbers itself is actually dependent on the rotation centers. But then if you look at a monolayer, the electrons and the holes, their states are sitting in the same layer, so no matter which choice you made, the relative, the difference between the electron and the hole quantum numbers in the optical transition, that one is independent of the rotation center. So in the monolayer, the transition must be associated with a definite selection rule, right? So in K, that's left-handed, and minus K, it's right-handed. But the situation becomes very different when you go to the heterostructure, where the electron and the hole are separated into two opposite layers. And then this rotation center dependent phase winding becomes relevant. So just think about, let's fix the rotation center at this point in the whole layer. But then depending on how this electron layer is stacked on top of it, this center can correspond to, for example, one of these three different situations. And they correspond to different windings. So that means the selection rule would be different at this distinct stacking. So you can have a K-value excon coupled to left-handed polarized light or right-handed polarized light, depending on the stacking. And in some situation, the optical coupling is just forbidden because of this phase widening does not satisfy the selection rule. Okay? But then you consider in a long period Maury pattern, we have local regions that approximately correspond to this lattice matched registries, except that the local registry can vary over a long distance between these different stacking. So that means if you look at the Excon with a fixed Valley or spin index, its selection rule can be spatially different at different places in the Maury supercell. Okay? So that's the optical coupling of interlayer Excon, the Maury modulated selection rule. Besides the selection rule, besides of this selection rule modulation, we know that interlayer Excon can also have a modulation in the energy. So in this Maury, because of this atomic registry change, the band gap can have a distinct dependence on the registry. So here is a comparison of the ST measurement by Kenshi's group and also DFT calculation. So it does show a very pronounced band gap modulation over 100 millielectron volt at different atomic registry. So that means if we look at interlayer Excons, so this band gap go into the Excon energy. So the interlayer Excon actually experience a superlattice potential. In the previous slide, we have just explained that at these different local minimums, Excon can have opposite selection rules. But then with this potential modulation, these global minimums are like a quantum dot confinement to Excons. So that's a 2D contour plot. So the blue ones are the lower energies. So these blue regions form the quantum dot confinement of interlayer Excons. So this Maury period can be like ranging from 10 nanometer up to a few tenths nanometers. So it's a fairly tight quantum dot confinement. And because this interlayer Excon have strong dipole-dipole interaction and exchange interaction, so when you consider an individual dot, the energy level diagram, so that's a 1 Excon state, 2 Excon states. And this interaction tells you that the cascaded photon emission from the 2 Excon state have distinct frequencies for the first photon and the second photon. This means this Maury defined quantum dot can be used as a single photon emitter or entangled photon source because we have two distinct polarization pathways. And the advantage of this quantum emitters, so quantum dot is it can be rather uniform, right? So Maury, if it's the Maury pattern usually have very good periodicity, so that gives you a rather uniform and highly ordered array of extonic quantum emitters. Moreover, these emitter properties can be programmed using electric field as well as using strain. So in addition to the band gap modulation, it's also from Kenshi's work, they also identified using STM the interlayer distance modulation by the Maury. And now we are looking at the interlayer Excon. So this distance modulation are carried into the dipole moment of the interlayer Excon. So if you apply electric field, the Excon energy can be modulated differently at different locals. That means you can use electric field, interlayer bias, to tune the potential landscape of the Maury Excons. So this is a zero field, but as you can tune it, you can actually shift the local minimum from this A region to the B region, where they have opposite value of selection rules. So that's electric field programming of this quantum emitter arrays in the Maury. Here I want to focus on this intermediate situation where the two minimums, A and B, can get energetically close to each other. So that effectively form a honeycomb lattice. But this honeycomb lattice is very different from the other artificial graphene system you can find. If you consider, so these two A and B lattice, they have opposite value optical selection rule, right? That's because of the local atomic registry determination of the Excon wave functions symmetry. And once you have this opposite selection rule, that necessarily means that the hopping between this nearest neighbor carry a complex phase. So if you work out a little bit more details, you can show this phase factor for both the nearest neighbor, the second and the third nearest neighbor hopping. So in this Mori, this is a general formalism for the hopping from one side to another. It carries a phase that is determined by this wave vector difference. So the two wave vector here are simply the one that correspond to the electron band edge and the other correspond to the hole band edge. And in the Mori, either due to twisting or due to lattice mismatch, the two band edge move away from each other, so you have this finite displacement. And this displacement determines these complex hopping phases. And because of this complex hopping phase, spin up has one phase shift, and spin down, as its time reversal, must have an opposite phase shift. So that effectively introduces a spin-orbit coupling, right? There is a spin-dependent complex phase. So if you look at any dispersion of the interlayer excons, the spin up and down have distinct dispersion. So you have a very large effective spin-orbit coupling due to this complex phase. So to understand this, we also find some interesting topological features. You have a fourfold degenerate Dirac node here and a two doubly degenerate Y node. So to understand these features, you can start from the graphene model. Right? Graphene model, we know there are Dirac cones at the corners of the Brillouin zone. But now we have this additional phase factor. This phase factor is like a shifter of the band in the momentum space, starting from the graphene model. So the shift happens in the following way. The two cones will just pick up this shift. So one goes to here, the other goes to here. So as a result, you have one cone at the gamma point and one cone at the minus k value for spin down. But spin up is in the opposite way. So overall, you have spin up and down cones at gamma point and spin up at k and spin down in minus k. So that explains why you have these topological nodes in the dispersion. And also there will be incomplete one-dimensional edge state that are connecting the nodes, but they, for the spin up and spin down excons, they happen at the distinct regions. So this is or you can also tune both the mass of the bulk excitons dispersion at this node region, as well as those topological edge states. So I will just skip these details. So that's interlayer excitons. Now I would like to go to the second example, so looking at the band inversion when the perpendicular electric field close this bulk gap and leads to hybridization of the these two Dirac cones from the two layers. There are two things that can happen when they energetically overlap. One is the trivial one. The gap remains finite, so that's avoided band crossing. And the other is a topological non-trivial band inversion, so accompanied by a band closing point and a reopen. And after it reopen, helical states will appear in this hybridization gap. So which of these two situations will happen in this heterobilayer when you close the band gap is also controlled by the interlayer atomic registry. So here we have two cones from one layer, upper layer and two cones from a lower layer, but we are looking at the hybridization between these energetically overlapping cones. So you can do a perturbation theory to get rid of this far-lying bands. But then you end up with 4 possible channels for the two hybrids. One is the direct coupling. The other is through some intra-layer, interband transition. Right? So the other three quantum pathways. But the key thing is that once an interlayer interband transition is involved, this transition is of a chiral form. It is proportional to the wave vector q, qx plus or minus iq1. So whenever such a interband transition is involved in a hybridization channel, that channel will lead to a topological phase transition when these two hybridize. So you can easily figure out that if these two channels dominate, you will have a topological phase transition, but with a different quantum spin Hall conductance in the inverted state. But if these two dominate, it will be trivial, because these two channels actually have opposite chirality, so they cancel. But then, which of these four channels dominate in a realistic heterobilayer is again controlled by the interlayer registry. So here we can use this rotation symmetry to analyze the possible channels again. So if you want the upper layer state to be able to couple to a lower state, the quantum number of the initial and final states must equal to each other. So then you can easily put, so for example, let's look at this high symmetry stacking. So the calcium atom sitting on top of the metal atom of the other layer. So for this one, you can choose this as the common rotation center. Then that's the two columns here in this table. So then you can compare the initial and final state. So three hopping channels are forbidden because they have different quantum numbers. And the only allowed one is this valence to valence band transition. Right? So then for this high symmetry stacking, only this interlayer hybridization channel is allowed. And there must be a topological phase transition once the band gets inverted. And then for other two high symmetry stacking that preserves the C3 rotation, they correspond respectively to these two situations. So then we can have this, we can also check out the R-type stacking and the similar conclusions. So this is a general picture. In a lattice matched heterobilayer, we can have all kinds of stackings that it can be parameterized by the interlayer displacement, right? The separation between the metal atom from the two layers. So this can span this phase diagram, right? This vector value. And these 3 points just correspond to the high symmetry stacking that preserves the C3 rotational symmetry. And our analysis tells us that these two configurations are topological insulators. These are the trivial insulators once you inverted the band. And then for other points in this phase space, you can show that these two topological ones are surrounded actually by a finite topological phase regions, while the blues are the trivial phases. So this shows how these topological regions appears as you invert the band gap by a perpendicular electric field. So here is the type 2 region, and as you apply the electric field, close the band gap, the two topological states start to emerge at these two high symmetry points. But as the inversion gets deeper, the topological regions also get to grow in size in this phase space. So that's for a lattice matched heterobilayer. We have this phase diagram. But then if you map this into the long period Maury pattern, so that's a schematic illustration, we have these local regions where the atomic registry is nearly indistinguishable from the lattice matched ones. And if we assume that their local electronic properties can be approximated by the lattice matched ones, then the conclusion would be I would have topological insulator electronic structure at these two regions, and other regions should be trivial insulated. So in other words, in this Maury supercell, you have this mosaic pattern of topological and normal insulators, where the helical states are expected to flow around these phase boundaries. So the phase diagram in the parameter space would be mapped into this real space in the Maury pattern. And moreover, we know this Maury pattern can be tuned by strength. In particular, the relative strength between the two layers. Just imagine you put the heterobilayer on top of a piezoelectric substrate. When you apply strain through the substrate, the two layers feel the strain differently because they are van der Waals coupled weakly. So one layer will be strained more than the other layer. This allows you to change the relative lattice mismatch between the two layers. And the Maury respond drastically to this relative strain. And you can, by a very small relative strain, you can tune the 2D Maury and stretch it in one direction and eventually tune it to one-dimensional Maury. And then the previous analysis is implying that in this case, we would have a two-dimensional arrays of a topological insulator quantum dots, and eventually to a one-dimensional array of a topological insulator nanostripes. And then you would expect helical states flowing at this phase boundaries that is defined by the Maury pattern in the bulk. So those are the pictures that you would expect from the local approximation, where we assume the lattice match heterobilayers electronic structure can locally describe the properties there. But to verify this picture, we still have to do a real space calculation. For this case, it's relatively easier, so we use this to demonstrate using a time-binding model. So that's a calculation for a fairly large period of the one-dimensional Maury. And you do find those helical states in the bulk gap. And the chirality of those states and their locations will correspond to the prediction from the local approximations. So the red regions are the topological regions according to the local approximations, and the green, blue ones are the trivial regions. And you have these in-gap states located, confined to this interface. And as you change the period of the Maury, those states can couple eventually through the finite size effect when the Maury gets small enough, and then the gap opens again. So the picture applies to relatively large Maury, and eventually, if you make the Maury really small, then everything becomes gapped again. This is a possible application of this Maury-defined superstructure. For example, it can make a new principle of transistors. That's off state, and when then you use a perpendicular electric field to invert the gap. And once the gap opens again, you get these helical states appear in the gap, hybridization gap. That would be the on state. These helical states that is densely packed in the bulk, defined by the Maury pattern, provide highly conducting channels. And you have this on-off switch by the interlayer bias. So compared to the idea of just using topological insulator crystal, where you only get one pair of channel per edge, the advantage here is you now have a densely packed helical states in the bulk, which is defined by the Maury pattern, and which you can also actually tune by the strain. So that makes the conductance more efficient. So before I go to a summary slide, let me acknowledge people that I work with on these things I discussed. So the interlayer Excon Maury package work is calculation mostly done by my postdoc Yu Hongyi, and the topological insulator part is done by another postdoc, Qin Jun Tong, and with the help of this student and postdoc. This is part of the long-time collaboration with the experimental group by Xiaodong Xu's group at Washington, which we try to understand the optoelectronic properties of these 2D semiconductors and the heterostructures. My former postdoc Guibing Liu and also former colleague Wang Yu, now at Nankai, they provided support on first principle calculations. And this is my summary slide. I think I will just stop here. Thank you.
Wonderful talk. Now open for questions.
Thank you very much for a very interesting talk. Okay. My question is about those topological phases and the edge states you talk about. We know that if there's a topological insulator, in our typical one, we have the bulk and the surface. It's a very clear cut because there's really a clear interface. So we talk about the surface states there.
Right.
Now, if you have a Moiré pattern, of course you could look at that and say, okay, this region is one kind of stacking, the other region is another type of stacking. It's in your figure there. If you look at the atomic structure, along the way, that change is kind of continuous. Okay, so I'm just wondering how you would be able to define the boundary.
That's a very, very nice question, very, very important question. So as long as the gap is not closed, you can always calculate this topological number, and it's quantized. I think the issue comparing to the you mentioned conventionally we have two different materials with a very sharp interface, and there is a very abrupt change of the gap. Here the gap actually changes smoothly and continuously. So it's color coded. So it's wide regions actually where the gap gets really small. But so here you can imagine you have a positive gap, and it crosses zero smoothly and becomes negative. And once it becomes negative, with the topological number jumps by a quantized value. So the effect of this smooth variation of gap compared to those sudden change of the gap is the confinement of this helical interface space get weakened, so that they have a larger extension in this direction. Right. It's a quantitative change. Yeah. So it's just simply changing a step potential into a smooth potential.
So you really have a gap crossing in your systems. You have metallic phases.
Yeah. In this region, the bulk gap is also very, very small. Yeah. So that's exactly the origin of these states. So if you see, those are the helical states, but you also have these states. That's originating from the bulk band, but since you have this smooth, quantum well confinement of the bulk state, they also give rise to these features. So that effectively makes the window for the helical states smaller. So if you have a sharp change of the gap, then those states will be moving into the bulk.
Maybe ask other questions.
It's okay.
Okay. Because without electric field in the first part of the talk, we're already talking about those edge states. I guess my question is there. It's not because in principle you could take a large supercell and do your pi binding calculations and solve those electronic states completely.
So those states, edge states, are actually the Excon edge states, not the electrons.
Okay. I see.
So that you're referring to these states.
Right.
So that's the Excon effective super lattice in the Moiré pattern.
Exactly, but even exciton, you have a continuous variation of the gaps.
Right.
So in principle, you could solve your pi binding and get all the electronic state for a huge unit cell.
We didn't do this for Excons. For Excons, we do the effective model. Because the band gap in this case, it always remains finite and large. Just you have this calculation of the modulation. So the band gap goes into the Excon's energy. So that's why it sees this high energy and low energy. And then we have this smooth potential landscape for the Excon. And then we work out the hopping of the Excons between those local and global minimums. And we do the effective time binding model. Effective time binding model, not the atomic time binding model, not the atomic ones.
But I guess my real question is how could you be so confident your model calculation will be getting the same results as your continuum time binding thing? because in principle, to solve the continuous time binding delay, look at all the band gap variations. And you got the, I mean, then you plot whatever in terms of the 2D decay, and you could get very similar result for your time binding for your exciton.
Right.
Also, right?
Right. So for excitons, because the wave function is still one-year type, so it has a fairly large extension still compared to the atomic lattice constant. So for excitons, the atomic scale type binding is I think it's too much, and this effective description would be good enough. You just figure out the large scale energy modulation by the atomic registry, and also you can analyze so just consider exciton wave packet confined because of this superpotential gap modulation. Then you just do the symmetry analysis, right? So this point itself is a high symmetry point. So the wave packet confined to this point, it has the C3 rotational symmetry that allow you to analyze the optical selection rule as well as the hopping phases between this A and B sites. So those features are sufficient to construct an effective or type binding model for excitons. So the atomic scale information are already captured by this, the rotational symmetry of the exciton wave packet, and that comes in as a, exciton's wave function has a fairly large extension. So it's a local information over the exciton's wave packet extension.
Okay, Professor Guo.
I find this is both helical state, isn't it?
You mean the exciton part or the topological insulated part?
The last part.
Last part, okay.
So my question is actually quite simple. Are this helical state each spin polarized?
So that's helical state. Spin up is moving this way, spin down is moving the other way.
You should have a quantum spin Hall effect.
Yeah, that's quantum spin Hall. Yeah.
And this is the bulk, not the edges.
Right. So the edges, because the vacuum has different topology from the bulk material. That's why you have edge state. But here, if you have a more redefined, local topological properties,
so you
can have many
so
pairs.
You have very high quantized conductivity.
That's the point. So comparing this to the crystal, the edge.
The crystal, topology is only
one pair.
You have many pairs.
Yeah,
conductivity would be very, very high.
Yeah, that's the point. Yes.
Oh, okay. As people think that.
Experimentally, not yet, because this material, the gap is still too large. So you need to apply a electric field that is close to the breakdown field to invert it. So we are looking for material combinations to begin with a smaller gap, or even inverted at the beginning.
Maybe for ditelluride, you have smaller.
Yeah, that's true. Ditelluride. Yeah. And combined with the other, so also change the transition metal atom may also help. But whether we can, form stable heterobilayer, that's still many technical issues to work on. Yeah.
Thank you.
But theoretically, it's very nice work. So in real case, right, when you really put two monolayers together, right, get a little strain or the disorientation, right, the real thing happening is somewhere will be relaxed.
Yeah.
And somewhere, right, then you really get a defect interface.
Okay.
And for the different regions, it actually looks very similar.
That's a good point. So that happens in graphene, right? Graphene, on boron nitride, in some small twisting, can get strained so that the other regions get mostly lattice matched, but the strain is relaxed at some edge. Yeah. If that happens, the general picture is still here, except that your phase diagram gets reshaped. So for example, you probably can, because of those location-dependent straining, the size of these topological regions can get changed, either larger or become smaller because of that. So the But as long as your the Maury period is sufficiently large compared to the the lattice constant, I think the general picture is still valid. But then for this TMD things, I think because it has 3 atomic layers, so it makes it rather difficult to do the graphene thing. So according to Ken Shi's experiment, it's more like the Maury pattern formed by 2 rigid crystals. But of course, you have this interlayer distance modulation.
So when you do the real calculation, how did you handle the interaction between the 2 layers?
Sorry?
I mean, interlayer
distance.
Right.
Distance.
Right.
So we are doing the type binding calculation. So interlayer distance goes into the interlayer hopping magnitude. Yeah. So this is just a. I don't think it's very yeah. Eventually, I hope first principle can be done, but it's a large. Very large Maury supercell, so it can be complicated. But I heard Guo Hong is developing some very powerful algorithms that can handle thousands of atoms per cell. So hopefully he can do the real calculations.
I think Hong Guo has one paper talking about this. Okay.
So, as you just mentioned, when you have this band inversion, your conduction band is basically localized on one layer, and your valence band is localized on the adjacent layer. So, given that, I mean, they are spatially separated from each other, how effective this inversion can be? Because you mentioned that there are different channels for the band inversion.
Right.
And then, if you have this band inversion, whether it can be described as an edge state or surfaces.
Okay. So you mentioned we have a band from one layer hybridizing with band from the other layer. So how efficient this hybridization is? So that efficiency is characterized by the magnitude of the interlayer hopping. So we have different hopping channels, but overall the magnitude of individual hopping channel is a few tens milli-electron volt. But then since it's a higher order process, so the effective hopping gets reduced by the, by further. So the gap opening in the hybridization is in the order of 10 milli-electron volt. So that's the gap that defines the region where you can look into those helical states. And those helical states, you always look for it at the boundaries between two distinct phases. In the bulk, you can do that in the bulk.
But there are edge states.
Yeah, edge state is for example here, if you have the edge is a topological one, then with a vacuum there's also edge state. So here I'm talking about edge state in a more generalized sense. Anything between two regions of distinct vacuum topology.
I guess my question is a follow-up question. From Professor Waals' question. I was wondering, in your conduction channel that you formed, how much conductivity can you actually squeeze out of your structure for practical consideration? That's my first question. I need a number, if you have one, for me. And the second question is, your material system seems to be very promising in terms of tuning inter-valley type transport. I was wondering, so far, have you looked into the properties of the magnitude of negative differential resistivity resulting from such inter-valley transport, if there's any? So those are my two questions.
Okay. So first, your first question, I think is asking about the conductance per helical channel. To answer that question, I think a lot of realistic issue has to be considered. disorders, and in particular, there are bulk states that is energetically close to those states. So as I discussed with Professor Cho, we have a smooth variation of the gap from the positive to negative. So there are bulk states that can be confined by the quantum well effect in this neighborhood. So we expect, unless you can make this hybridization gap sufficiently large, we have to take into account those bulk states that is also confined near these interface regions. So those are the issues that we need to address to get the realistic conductance. So we haven't done that yet. But I think ideally, okay, if you can open a very large hybridization gap, that's one direction that we are moving on. Just finding some material combinations with a large interlayer hopping, say from 10 millielectron volt to 100 millielectron volt. So then there should be energy windows that allows nearly quantized conductance per pair channel. I think the second question, I guess you are asking about the magnetoresistance that is people find in the wire semi-metal, or the.
I was thinking in terms of the potential of using your structure to form nonlinear resistors.
Okay.
And because you have so much control over the way that the carriers and can do intervalley type transport.
Okay.
I was wondering if you will observe very significant a negative differential resistance.
Yeah, we haven't looked at those things. I know I don't think people ever talk about the negative resistance in this system. So for carriers, what we have here is actually a well-gapped massive drag cones. So in modulator. Okay. And then my colleague Lu Haizhou has done some calculation about the intervalley scattering and how that goes into the magnetoresistance of electron or hole transport. But I don't think there is any negative signature of negative resistance has been identified yet.
Thank you for a very nice talk. So actually I have a very general question that so all your system actually involved with kind of very narrow region the electrons or hole can confine due to topological reason or other more geometrical reasons. So I wonder whether there is a kind of self-consistent calculation necessary to consider the intra and interlayer Coulomb screening?
Yeah, I mean, ideally, I think it would be nice if this electronic structure can be calculated from first principles. Here we are doing a type binding, taking things.
RPA type binding, you can do that. So kind of a Coulomb interaction.
Right.
You can do it because it's very easy to kind of relax the structure to relieve the Coulomb interaction in this system because interlayer interaction can be varied as you relax the structures to reduce the Coulomb interaction. Right. So it's very sensitive to each other.
Right. So for the Excon ones, I think the factor you were mentioning is relatively easier to take into account. We have this distance modulation that must go into interlayer Coulomb interaction. But then since we are looking at a long period Mori, right? And the Excon's wave function, a wave packet, it's large compared to the unit cell lattice constant, but it's small still compared to the Mori size. So in that limit, we can start from a lattice matched layer by layer and taking into account the Coulomb interaction at that level, get the Excon energy and also transition dipole moment. That will be the two parameters. Then we can put into this Mori modulation to do the next level effective model calculation.
Okay, this one.
Nice talk. I have a question. When you study Excon in bilateral heat junction, do you study like the temperature dependence? For example, like the temperature dependence of absorption spectrum, emission spectrum, or reflection? Yeah.
So I think you asked about this temperature dependence of the Maury. Yeah, I think that is one reason that this Maury feature that need to be well understood to understand the temperature behavior of interlayer excons. My collaborators and other groups has done many ensemble measurement of the photoluminescence from interlayer excons. And actually they see some very peculiar features including temperature dependence, wavelength dependence. But if you put this into the picture that I described, you have this super lattice potential modulations. Then the dynamics in this super lattice potential plays a key role in affecting the temperature dependence of the light emission properties. So that's still need to be understood. So it's a problem of understanding the dynamics in this Maury potential to use that to interpret the experimentally observed temperature dependence.
Okay, due to time limits, let's thank Professor Yao again.
Thank you.